data structures describes approaches to organizing data in computer systems, whether the data is stored in RAM or on disk. In fact, data structures concerns organizing information in huge systems. Those could be large, centralized database systems for big multinational corporations, indexing the trillions of bytes of web material on sites such as Yahoo or Google, or huge distributed database systems with multiple nodes scattered across vast networks. The goal in organizing data is to provide the easiest path of access to information at the fastest possible speed. Click on the sound file icons beside each question to see the answer. This unending quest for efficiency, this quest for better performance, why does it matter? Let's consider an example based on your own personal experiences. You undoubtedly use search engines such as Yahoo or Google. A search engine website such as Google indexes trillions of bytes of data. When you use Google to find information, you expect to find what you want, and more importantly, you expect to find it with sub-second response times. And if Google can't provide that kind of accuracy and performance, you'll move over to some other search engine. Now, change your perspective. Imagine you're one of the architects of the Google search engine. If you can't satisfy users' expectations for accuracy and performance, they'll move to your competition. Ultimately, the life of your corporation depends on your search accuracy and efficiency. Consider another example. Imagine that you've just received your cell phone bill, and it contains several outrageous charges. You call the centralized office center or call center to dispute those charges. When you speak to an agent, after giving your phone number, you expect him to be able to respond to your concerns about the account. The ability to respond quickly and accurately to your concerns is absolutely essential. In the face of poor performance, you, the consumer, the customer, may simply move over to the competition. Again, the corporation's success depends on timely, accurate access to information. So, we know that efficiency matters, but how do you know how efficient your programming algorithms really are? How can you compare two different approaches to solving a problem? The final question is, how do you measure? And the answer to this one will allow us to compare different algorithms. Well, that's what the big O is all about. The O in big O is short for order of magnitude. Over the next few screens, we'll explore how the big O is determined. Here's a simple counting loop. Let's imagine that the goal in this program is to get I from 1 to 1,000. Obviously, the loop will require 1,000 iterations. On the next screen, let's make a small change. We're still working with this simple counting loop, but this time we've doubled the goal. We're going to 2,000 instead of 1,000. Naturally, because the loop is a simple counting loop, we must perform 2,000 iterations, or double the work. And if we were to double the goal again, this time to 4,000, then we'd require 4,000 iterations of the loop. As you can see from the absolute measure of efficiency, the algorithm effort is directly proportional to the change in the goal. In this case, we consider a goal of 1,000, then 2,000, then 4,000. To simplify our discussion, we'll refer to these changeable numbers as n. Notice the third column in the table. It shows that when we moved from 1,000 to 2,000, we required twice the effort to reach the goal. Similarly, when we moved from 2,000 to 4,000, that is doubling the number of items, again we required twice the effort. But this is pretty obvious stuff, right? Well, let's consider some loop variations, and that's next. This loop is nearly identical. We still have the same goal, that is, getting to 1,000. Remember, we'll refer to this as the value of n. While nearly identical, this time the loop counts by 2, rather than merely incrementing by 1 each time. Is this second case more efficient than the first? Well, of course it is. This loop requires only half as many iterations to reach n of 1,000. But how do we quantify how much more efficient? That's an important question, which we'll answer in a moment, but let's explore case 2 a bit more on the next screen. Like before, we've changed the value of n, doubling it from 1,000 to 2,000. The loop is still counting by 2, so the number of iterations is always 1/2 of n. But notice column 3 in the table. This is important. Notice that the effect of doubling the value of n, that is, moving from 1,000 to 2,000, means that we double the effort. We're going from 500 to 100. And similarly, when we double the value of n yet again, going from 2,000 to 4,000, we double the effort again. So while we know that this case 2 linear loop is more efficient than case 1, because we're counting by 2, we see that the change in program effort is still directly proportional to the change in n. If you were going to graph this case 2 relationship, you'd have a straight line. If you graphed case 1, you'd also have a straight line, although the slopes of the lines would be at slightly different angles. On the next screen, let's apply some of these observations to the big O. As I said earlier, the O in big O is a measure of the order of magnitude. With big O, we don't care about the specific value of n. Instead, we care about how an algorithm changes its performance as you change n. So, with the 2 linear loops considered earlier, when we changed n by doubling it, the loops required twice as many iterations. In that sense, case 1 and case 2 are deemed to have the same big O. Even though case 2 is somewhat more efficient than case 1, the difference is considered insignificant. Next, we'll consider some other loop variations. Again, our goal is 1,000. That is, n is 1,000. Again, we start at 1, but this time the loop doubles the counter variable I on each iteration. Notice the big difference from our linear loops. Here, after 10 iterations, the value of I has surpassed 1,000. In fact, it is 1,024. Remember, in case 1, we required 1,000 iterations to get to 1,000. In case 2, we required 500 iterations to get to 1,000. But remember, about big O, we don't care about the actual program effort for a given value of n. No. Instead, we care about how program effort changes as we change n. So in the next screen, let's consider the effect of doubling the value of n, much as we did for cases 1 and 2. Wow! Take a look at this. This represents a huge difference. With the logarithmic loop, or one that multiplies the counter variable on each loop iteration, we show much less effort. Each time we double the value of n, for example, moving from 1,000 to 2,000, we increase the number of iterations by only 1. This is vastly different from the linear loops we considered first. And if we double the value of n yet again, moving, say, from 2,000 to 4,000, the number of iterations increases by only 1. Here's a slight variation on the logarithmic loop. Instead of multiplying on each iteration, we're dividing. So the loop starts at 1,000 and works its way down to 1. And notice also that we're using integer-based arithmetic, so some division results in truncation to a whole number. Much like the previous logarithmic loop, where we multiplied by 2, 10 iterations gets us to our goal. On the next screen, let's consider again the effect of doubling the value of n. Again, with this logarithmic loop, one that divides the counter variable on each loop iteration, we show much less effort than with the linear counting loops. Each time we double the value of n, for example, moving from 1,000 to 2,000, we increase the number of iterations by only 1. This is vastly different from the linear loops we considered first. And if we double the value of n yet again, moving from 2,000 to 4,000, the number of iterations again increases by only 1. Well, you might be thinking, so what? Loop 1 goes from 1,000 to 1. Obviously, the loop that subtracts 1 takes longer than a loop that divides by 2. The loops are doing different things, right? No, wrong. They have the same goal. They're both moving from 1,000 to 1. The algorithm is different from each loop, but the goal is the same. Let's take a concrete example to try and clarify the assertions that I made on the previous screen. Consider the common problem of coiling a rope. Now, I want you to think about how you're going to approach taking a rope and organizing it neatly so that you can store it. There's actually several ways of doing it. I'm not sure how you were planning to coil the rope or to organize it, but there are two different approaches that I describe here. In the first case, you could loop the rope around your arm, one coil at a time. Now, this is probably the most common way that people would organize a rope. But the second way is one where you divide the rope in half again and again and again. And here's the key concept. With coiling a rope or organizing a rope, you've got the same goal, but there are different algorithms and different efficiencies. One algorithm is linear, where you coil it around your arm. The other algorithm is logarithmic, where you continue to divide the rope in half again and again and again. And as the rope lengthens, you find that there becomes a radical difference in the effort needed to organize the rope. Let's explore these two different approaches using some real numbers. Let's assume that you have a 100-meter length of rope. Each loop in the coil is going to be, well, about 1 meter. So with the first approach, where you're looping it around your arm, it's going to take 100 iterations in order to coil that rope. With the second approach, where you divide the rope in half each time, you're only going to have, about 6 or 7 iterations. Up to now, we've only been considering simple loops, whether they are logarithmic or counting loops. But most algorithms aren't quite so straightforward. You'll find that most algorithms have some nesting of loops, and that's what we'll consider now. So take a look at this simple program. We have 2 loops. Again, the goal is 1,000. That is, n is 1,000. And we're starting at 1 again. The output, or the program iterations, when we start with a value of n 1,000, then it takes 1,000,000 iterations. When we have a value of n 2,000, it takes 4,000,000 iterations, and so on. But remember about big O. We don't care about the actual program effort for a given value of n. No. Instead, we care about how program effort changes as we change n. So, going back to the chart, take a look at the effect of doubling. When we move from 1,000 to 2,000, the program effort changes from 1,000,000 to 4,000,000. That is, it's 4 times the effort. Similarly, when we double again from 2,000 to 4,000, then the program effort changes from 4,000,000 to 16,000,000. 4 times the effort. Now, in the next slide, let's consider what happens when we triple the program effort. So with this slide, we're going to triple the value of n in each case and watch the change in program effort. Remember, we don't care about the actual specific value for program effort for a given value of n. No. Instead, we care about how program effort changes as we change n. The key word here is change. Take a look at the chart. When we have a value of n being tripled from 1,000 to 3,000, then the program effort changes from 1,000,000 to 9,000,000. Similarly, when we change n from 3,000 to 9,000, that is, we are tripling the value of n, then take a look at the program effort. It changes from 9,000,000 to 81,000,000. We have 9 times the effort when we tripled the value of n. But let's consider what's involved with quadrupling on the next slide. Again, we're going to watch the change in program effort, this time as we quadruple the value of n. Let's see how program effort changes. Looking at the chart, moving from 1,000 to 4,000 for a value of n, the program effort changes from 1 million to 16 million. Similarly, when we change the value of n from 4,000 to 16,000, program effort changes from 16 million to 256 million. In all cases, 16 times the effort. Let's summarize on the next slide. Our previous program had two nested loops, each of which was a counting loop, and that's considered to be a quadratic kind of algorithm. How do you calculate the efficiency? Well, each single iteration through the outer loop requires a complete set of iterations of the inner loop. Now, because the outer loop had an efficiency of n, and the inner loop also had an efficiency of n, when you have nested loops, you must combine the efficiency. That is, multiply each nested loop. Thus, we have an efficiency of n squared. And in fact, we saw that when we were taking a look at the effect of doubling, tripling, and quadrupling the value of n. When we doubled, the program effort increased 4 times. When we tripled, the program effort increased 9 times. When we quadrupled, the program increased 16 times. So that's where you can see that n squared relationship showing up. Here's another simple piece of code with two nested loops. Although the loops are a little different, notice that the outer loop, I, is a counting loop, and the inner loop, j, is a divide by 2 loop. So, in order to calculate the overall efficiency of the algorithm, the outer loop has an efficiency of n, since it is a simple counting loop. The inner loop has an efficiency of log n, since it's a divide by 2 loop. We multiply the two efficiencies because they are nested, and the absolute measure of efficiency is n log n, merely multiplying the two components. So far we've dealt with some pretty simple examples, simple loops counting or logarithmic, or nested loops, independent nested loops, which again could be linear or logarithmic. Well, let's consider something a bit more complex. In this case, we have two nested for loops, and this one is called a dependent quadratic. And that's because the outer loop, I, well, that's a pretty straightforward counting loop, but the inner loop, j, is dependent upon the value of I in order to do its work. So this one's not quite as straightforward. Let's take a look at how we go through an analysis to decide what is the level of efficiency for that kind of algorithm. When we actually count the number of iterations through this program, we can see that when I is equal to 1, then j only goes through its loop once, and the next time through it goes 2 times, the next time through 3 times, the next time through 4, and so on. So with a value of 10 for n, then these two loops go through 55 total iterations. And the absolute measure of efficiency is shown there as n parentheses parentheses n plus 1 close parentheses divided by 2 parentheses. However, that's more complex or more detailed than is necessary. And we can simplify that in order to compare this algorithm with the other algorithms. This is where the big O comes in, because the big O is a tool which we can use to compare different algorithms, algorithms which may have significant complexity, and what we want to do is try and distill that complexity to the simplest expression of efficiency. What we really want to do is find out what really matters in measuring efficiency. And the O in big O really just stands for order of magnitude. So in a simple case like the two nested loops that were both counting loops, where we had a quadratic style of algorithm, we had an efficiency of n squared. And that's written as a big O of big O open parentheses n squared close parentheses. When taking an expression of efficiency and simplifying it to its big O value, you'll end up with one of the things that's listed here. The fastest, or the most efficient, is big O 1. The worst, big O n factorial. And it can be anything in between. Big O log n, big O n, n log n, and so on. So ultimately, it's going to end up being one of those kinds of expressions. What process do we go through? Well, it's essentially a two-step process to simplify into big O. The first is, take a term, each of the terms in the expression, and set the coefficient of each of those terms to 1. Step 2, we want to take the largest term and throw away the others, because the other terms are not significant. Now that sounds a bit abstract. Let's take a look at how you'd apply that kind of process in simplifying the dependent quadratic measure of efficiency that we looked at earlier. As you can see at the bottom of the screen, dependent quadratic is n open parentheses n plus 1 close parentheses divided by 2 close parentheses. So we want to take that and simplify it to one of the simpler expressions of big O. Well, let's go through the process of simplifying the dependent quadratic expression of efficiency. First step is, let's expand the expression so that all terms are shown without any parentheses. Step 1, we eliminate the innermost parentheses by dividing those two terms by 2. Next, we eliminate the second set of parentheses by multiplying the n across all terms. And we're left with this fully expanded expression, n squared divided by 2 plus n divided by 2. We'll now take the expanded expression and apply the two steps which are used to simplify for big O, where we set the coefficient of each term to 1 and then keep the largest term, discarding the others. Step 1. We set the coefficient of each of the terms to 1, and we're left with n squared plus n. Step 2. We discard the least significant terms, in this case n, and we're left with n squared. So n squared becomes our big O measure of efficiency. Using the rules described earlier, you try simplifying an expression. Take a look at this one, n plus n squared plus n3. What would be the corresponding big O for this? There were no coefficients, so we didn't have to change that. But there were 3 terms, and we needed to discard the 2 terms which were least significant, and left then with n cubed. And now try simplifying this one. 6 log n plus 9n. Start by discarding the coefficients, or rather converting the coefficients to 1, and you're left with log n plus n, and then taking a look at those 2 terms, discard the ones which are least significant, that's the log n, and you're left with n. So this particular measure of efficiency simplifies to just big O n. This time, let's try and find the big O for an actual algorithm. On the left-hand side, you can see some pseudocode, a couple of nested loops followed by another loop. So, in order to find the big O for the entire algorithm, there are several steps. The first, find the efficiency of each loop. You can see that there are 3 loops there. The first, or the innermost loop, is an n loop. The outer loop in the first one is order n, and then the last loop, because it's a divide by 2, is log n. Step 2, combine all of those different measures of efficiency. When you have nested loops, you multiply. When you have sequential loops, or loops that are one after each other, you add. And so we're left with n times n plus log n. Step 3, we'll simplify. The first part of simplification is taking the n times n, converting it to n squared. And so we're left with n squared log n. And the final stage of simplification? Well, we have n squared plus log n. We throw away or discard the term that's least significant, the log n, and we're left with n squared. Hence, the big O is n squared. For those of you who are more visually oriented, a graph like this may help. Take a close look at the x and y axes and what they represent. On the bottom, the x-axis is the number of items in the data set, and it's a linear scale. On the y-axis, it's the number of processing steps to complete a particular task. Again, a linear scale. So, essentially, we have n on the bottom of the screen, or bottom of the graph, and on the left-hand side, it's the level of effort. The goal, of course, is to keep the curve, or to keep the graph as low as possible, because the higher it goes, the more effort is involved. And pretty clearly, big O1 doesn't move. It's flat, right at the bottom. So that's the ideal measure of efficiency. The next one up, log n, which starts off growing, but then quickly begins to flatten out. Big O(n) is a linear scale because the effort is directly proportional to the value of n. And then you have n log n, n squared, and 2 to the n, which have increasingly laborious levels of effort. Some of you may get a better handle on how big O works and how efficiency compares by taking a look at some hard numbers. In this case, we're talking about algorithms of different types, logarithmic, linear, logarithmic, and so on, where we have a value of n of 10,000. We're also assuming that this is running on a fast computer. So in the case of logarithmic, a big O log n, when we have an n of 10,000, we only have 14 iterations, and the estimated time to complete is in microseconds. Pretty impressive. When we move to linear, big O(n), then with a value of n 10,000, we have 10,000 iterations. And when it executes on a computer, a fast computer, it's going to take maybe, a tenth of a second. Then when we move to linear logarithmic, big O(n) log n, 140,000 iterations, and the estimated time is 2 seconds, and so on. As the value of n grows, the difference between the logarithmic at one extreme and the factorial at the other extreme is quite dramatic. Just how dramatic is the efficiency problem when you get up to an exponential algorithm? Well, take a look. When we have an n of 10,000, that's 2 to the n. The term intractable means that no matter how fast your computer is, it's not going to finish. So, take the exponential case with n equaled only 1,000, not 10,000, just 1,000. Given this very fast computer, it would take 3.39 times 10 to the power 288 years. The age of the universe is estimated to be only 1.5 times 10 to the power 10 years.